My name's Mark Carey. I work for Mental Graphics within the embedded software division, and I'm a technical marketing engineer working with some of our virtual prototyping technologies and tools. And today I'm going to talk about how some of the virtual prototyping technologies that are available today can help with performance analysis and in general. So going back to why we might need virtual prototyping, if we take a look at hardware and software development as independent flows, then in general they're in quite good shape. They're well understood. They've been around for many years. We've got well-established tools and facilities available for people to develop these as independent kind of deliverables. But especially in today's world, where we have to build things quicker than ever, and time to market is very important, we have this pain point where we have the integration of the software and hardware coming together, usually being the bottleneck of the whole process, and problems are found too late in the life cycle, and we have to iterate, and changes cause us trouble with the whole design flow. So this implication of integrating the hardware and software is the critical challenge. We need to find new ways to help us verify the performance and the power as early on in the life cycle as possible. So the traditional flow is for software teams to have to wait for some real hardware to become available, whether it's a prototype board or the final product. So this causes scheduling problems. We have to wait and can only start when the hardware is ready. On top of that, normally it's hard to set up the hardware. It requires lab environments, loads of cables, probes, and serial connections, and also tracing and capturing and understanding the performance of the final hardware is quite difficult, and it's also an intrusive process because we may have to instrument software code which changes the behavior and the results that we get from our simulation runs. Or in the case of real hardware, it's the real execution of the software. So just to give some examples of the problems about debugging and analyzing using real hardware, if we take an example of adding a single printf statement to some embedded software, then you can see that a single printf might impact the runtime performance of the software quite considerably, and then that would skew all of the analysis and performance data that we get back because we're not really testing the final release software because we've instrumented it with maybe printfs. Or another example is to use LTTNG. Again, we can see that instrumenting the code with this system impacts the performance, a 3x performance impact, and the actual image, the software image that you're going to upload to these hardware boards are significantly bigger. Maybe they won't even fit into the available RAM. And there's other problems such as like core sight. It gives you tools, but it might impact the amount of power that the system takes, and so it's hard to analyze that. And these services are most often only available once the bootloader has completed. So to help us resolve some of these issues, we can start thinking about using a virtual prototyping flow to change this kind of design flow and to enhance what we can do. So if we move to this, it's quite usual to have a hardware group that's responsible for creating the models to assemble into a TLM platform. So the hardware group normally focuses on building models to model custom peripherals that are built in-house, and then along with those, using third-party models, a platform can be assembled which can be then used to debug the hardware and get performance and power analysis from it, and also to debug the platform at this early stage. Meanwhile, whilst these system C or models are being created, the RTL verification can start, a UVM test bench framework can be constructed, and the system C models can be used as part of this test bench. And then once the platform has been validated, it can be supplied to software development teams to start to use to really develop and debug the real world software upon without having to wait for some real hardware. So using this virtual prototype, that can be achieved. And using that, we can actually analyze both the hardware and software running together using some non-intrusive capabilities to gather analysis data without actually impacting the software that we're actually running on the virtual prototype. So just looking and describing some of the concepts that's involved here. Normally a virtual prototype's constructed using some kind of standard methodologies and technology. Most often the language that the platform is describing is System C together with TLM 2.0. So this allows both timing and power attributes to be modeled within the system. And it also gives us the understanding of different communication protocols and busing structures, memory architectures, which helps us build an accurate model of what the hardware should do and how it should perform. So it's important that these platforms are deterministic. Every time you run them, we want the same behavior to happen. If a bug's found, we need to be able to repeat and reproduce that bug. So that's a very important aspect of it. And by using System C and TLM, we kind of get debug capabilities to allow developers to have full visibility into the hardware. So we can see the registers, we can see how the hardware is behaving in conjunction with the software that's running upon it. So there are kind of many different use cases when we start to use a TLM environment in conjunction with System C. So we can, this ranges from doing a pure performance analysis at a high level down to a fully functioning platform that you can run software on. So there is a concept which we call scalable transaction level modeling, and this allows the functionality and the timing and power and the communication layers to be kept separate from one another. It also allows you to take functional models, maybe existing C++ code, wrap them very easily around the communication layer, and then add timing and power policies on top of that to automatically generate the performance aspects of the model. So this kind of eases the mechanism to create accurately timed models without having to hand create lots of System C, lots of complicated timing and power code. This can be abstracted away using this mechanism, which we call timing and power policies. So as well as kind of this split of a model, it's also possible to run a platform either in what's called LT, loosely timed mode, which enables the fast simulation and is most appropriate for running real software on. It's also possible to switch to what's called the AT, approximately timed mode, where the simulation runs much slower, but in this mode we're capturing all of the timing and power information so that we can analyze that data. So it's important to be able to switch between these two types of mode so that we can have a fast, maybe an operating system boot, and then toggle to capturing information when we're ready to capture, depending on the types of application we want to analyze. So typically the best approach to actually validate a platform is to run some real-life software upon it and use that as the stimulus for the platform. So for example, if we can boot Linux and load real-life device drivers and applications that access the registers in the custom peripherals that we've modeled, then we can be more confident that the platform is working correctly. At least we've got the boot up stage working. So like I described before, we can capture data at certain points during the execution of the platform. So we can toggle between these two modes of simulation. And in fact here, the graphic displays a Linux boot. We're not interested in analysing the performance of the Linux boot. It's out of our hands, maybe. So we run the simulation in LT mode. Then at the point in time that we're ready to analyse our real applications that are going to run on the platform, we can toggle to the AT mode to start capturing the timing and power aspects of that. So typically in a LT fast simulation mode, we can show and record the transactions, so we can visualize those as spikes on a waveform, whilst in AT mode we're actually capturing each transaction with the correct sequence and a duration based upon the timing and power policies that have been applied to each of the models. So as well as having kind of timing capability and analysis, it's also important these days especially to understand power usage and to help optimize the amount of power that's being used. Historically, people have been using things like complicated Excel spreadsheets to help budget the amount of power spread throughout a particular architecture. But our virtual prototyping tools give us more capability to help us understand where the power is being used, in which pieces of the platform, and by running real software on the platforms, we're getting more accurate results. So we're not just guessing where the power is used, we're actually running some real stimulus on this platform so that we can get better estimations and to help us budget where we can use more power in certain peripherals or less power in others. So, like I mentioned, each model you can assign power policies which specify the amount of power each transaction will use as it enters and leaves the particular models. So obviously the power that's used is also dependent on the amount of data that's being processed and sent between each of the models on the platform. Once the simulation has been run, you can analyze and get different views. So for example, you can see the power distribution to show the total amount of power that the whole platform is using. And then you can also see exactly how much power each of the pieces of the platform, all of the IPs, what they're using at the time of the simulation. You can also see things like bus throughputs to understand the traffic that's going through the platform. So the nice thing is that the timing and the power policies and the parameters can be changed very quickly and dynamically. So you can rerun a simulation without having to rebuild or relink the TLM System C platform. This gives you a quick and kind of an iterative approach where you can run multiple simulations and then compare the results alongside each other on the same graph to help understand where the bottlenecks are and what kind of models are using more power, and you can kind of iterate and change the behavior. So sometimes you might already have IP that's defined in RTL, and in this case, instead of having to effectively reverse engineer RTL into System C, it would be ideal to be able to use the RTL, but if we start to simulate RTL in a software-based simulation, obviously the simulation speed grinds to a halt and things become so slow that it doesn't realistically enable software to be run on them in real-time speeds. So we've actually got a couple of solutions available to help solve this problem. One of them is to build what we call a hybrid co-emulation virtual prototype. So this is where the RTL can be part of an emulation, and we join the TLM platform to the emulator. We kind of keep things separate. It's a client-server based mechanism so that the time-in engines are separate. They kind of synchronize together, which means that the software can run at the TLM speed on the TLM platform, and your custom peripherals within the emulator will run at the emulation speed. So it's the speed is kept up as much as we can to keep a fast environment. In fact, the same setup can be built and engineered with a software simulator so that you can build and configure their environments without hogging up an emulator resource. So this is the matching configuration, the simulation and emulation. And once you have this environment, you can actually build a virtual prototype to deliver to software teams. So whether it's a pure TLM-based platform or whether it's a hybrid, it's transparent to the software development teams where the actual devices are implemented, whether it's ending up on an emulation box or modeled within TLM System C. That becomes transparent. And likewise, we have technology to bridge the TLM world to an FPGA board. So again, this is useful if you have existing RTL that you want to keep as RTL. And obviously having and using the RTL is the most accurate model because it is the thing that's going to end up on the real hardware. So in the case of the FPGA bridge, we've actually got technology which can bridge via like a bus infrastructure, such as an AXI bus, so that the TLM transactions gets mapped over onto the AXI bus of the FPGA board and then back to the TLM when required. So this kind of combination of using the TLM with some real hardware maximizes the execution speeds, but gives you your model availability because you may already have RTL, and it obviously is accurate because it's going to be ended up in the real hardware. So as well as helping the software developers, the System C TLM platform can also help with the RTL verification. So this enables the verification team to kind of start work early in the design process. They can use the System C models within a UVM test bench environment. So the test bench framework can be built along with the stimulus, and instead of waiting for the RTL DUT to be existing, we can use the System C DUT. So it proves that the stimulus is going to be sufficient to meet the coverage, and it also helps validate that the System C is correct and has implemented all of the correct registers that were specified. So it gives a nice head start to the people developing the RTL test framework. Once the RTL DUT does become available, then in fact the System C can be switched out, and it can be kept as a reference model, so it can be used along with a scoreboard to kind of prove that the RTL is implementing the same behaviour. So it keeps the test bench and the stimulus is the same. It's exactly the same. So it just helps with the process of building the framework and the stimulus, reusing the System C model, switching it out when the RTL becomes available, and helping with the verification of the RTL as we've got something already built that should be the same behavior. So once we have a fully functional and validated TLM platform, we can create a virtual prototype which can actually be delivered to the software engineering teams. It's important to avoid frustrating the software developers. So this virtual prototype must run software at speeds roughly the same as actual hardware. And it also must seamlessly integrate with the typical software IDE that the software developers are using. So this means that the same build process and the same software images are equivalent to what would be done using real hardware. With the same software development process is used to build and debug and develop software running on one of these virtual prototypes. But as well as behaving like the real hardware, we can gain extra value by using a virtual prototype. So things like seeing the hardware registers, things like debugging complex software and hardware interactions, understanding what's going on in the hardware side, and having the ability to optimize the software to meet the performance and the power goals. Having this visibility is all achievable using a virtual prototype. So typically within a TLM platform tool, it's possible to generate this virtual prototype. You can normally generate either a Windows or a Linux-based virtual prototype depending on what the software team is using in terms of their tool set. The actual prototype should execute in the same manner as a TLM platform, but because it is just a virtual prototype, the architecture of that prototype cannot be changed. It's a static architecture. So there's normally some kind of GUI within the TLM platform tool to help produce one of these virtual prototypes. However, I said that the architecture of the platform cannot be changed, the topology, but it is possible to manipulate and configure parameters that are exposed to the platform. So this can be done by using something like a parameters file to configure pieces of the platform. So for example, you may want to change clock speeds or cache sizes, memory sizes. You might want to disable whole IPs if you're not interested or you don't want to use them. And quite often it's useful to configure things like the bus memory addresses where peripherals are mapped to, so that you can change software drivers and how things are set up depending on what's being developed in the software side. Of course, sometimes the hardware team does not want to give that level of flexibility over to the software team, so this kind of configurability can be restricted and kept hidden if that's what's wanted. So some of the benefits of using a virtual prototype is that unlike real hardware, which can suffer from glitches or environmental issues and things like that, the behavior of a virtual prototype is actually fully deterministic, so it's fully repeatable. When you hit a breakpoint, everything stops. All the stops are clocked. Clocks are stopped, so that you can see a true visibility without things running on in the background. Just like within a TLM platform, you can actually toggle between the functional and performance execution modes depending on what you want to analyze and the data that you want to capture. We also have things like semi-hosting facilities, so you can write and control the hardware without having to rely on perhaps like a UART console to get some debug messages out. You can just use a semi-hosting call to output a message without having to use some kind of UART. So it gives lots more chance to debug and develop software, and it's a nicer way to do that. Quite often it's important to be able to connect kind of real-world I/O with one of these virtual prototypes in order to get some kind of real stimulus into the platform and also to get some results out. So we normally have some type of I/O model as part of a platform, whether it's an Ethernet device, USB displays, keyboards, etc. So these actually behave exactly the same as real hardware. So if you have a virtual prototype that may be booting up Linux, then this, if it includes an Ethernet model, gives you the chance to maybe secure shell log into it or FTP onto it, just as if it was a real hardware board. We also have the capability to map the USB ports on your host machine into the virtual prototype, so it becomes easy to attach real hardware in the loop effectively by bridging the host hardware to the virtual prototype. Quite often these days, graphical displays are used, things like automotive applications. There's many places where you need some kind of graphical output. Therefore, it's important to have some kind of display technology. Now, to model a whole GPU is incredibly complex. So what is available is technology to actually bridge and catch OpenGL software functions and bridge these to use your host machine's GPU. So this then increases the simulation performance. It gives the virtual prototype the performance needed to keep a fast and real-time runtime kind of operation. And we can still analyze and capture timing and power events based upon the amount of time your host takes. Obviously, it's not going to be 100% accurate compared to maybe the GPU that's going to be ended up in the target, but it gives you a good step towards that analysis. A typical software IDE should continue to provide, the standard set of breakpoints and stepping through embedded code, just as it would run on a real piece of hardware. You often would have some kind of manager to import a virtual prototype into the IDE, so that the IDE is then aware of the new target. You would probably see some kind of register view to allow you to see all of the registers that are available, not just the registers that are visible from the software perspective, but in fact all of the registers that are defined within the hardware platform. So as well as setting breakpoints on the software code, you can also, or you should also be able to set breakpoints on the hardware. So when a hardware register changes, you need to be able to break and understand the state of the system. So that gives you extra facilities and extra value that you wouldn't achieve if you were just using real hardware. And then a really powerful and great benefit of using virtual prototyping is that it gives us a chance to non-intrusively collect performance data. So we can trace and profile without any form of instrumentation. We don't have to recompile the software source code, so that the results that we get from analysis are truly aligned with the release version of the software image. So we're not going to be changing the image size or impacting the performance of the software image at all. So this kind of mechanism is made possible because the virtual prototype is in control of the instruction set simulators. So we understand exactly what each core is doing. And when each function is executed on each core, we can actually trace and track that automatically. We can also use this mechanism to inject extra code to impact the behavior or inject faults into the software. And because, again, this is non-intrusive, so it's not actually impacting any of the data and the analysis results that we're collecting as we run the simulation. And all of this is dynamic, so we can actually enable or disable tracing of particular functions at any point of time during the execution of the virtual platform. So it's easy to target specific areas of software code that you may want to profile. By having it as a dynamic system, you can pinpoint problems and only collect the data that you're interested in, as opposed to instrumenting the whole thing and having a lot of data to analyze, which becomes overwhelming. This non-intrusive capability allows you to quickly pinpoint the bottlenecks and without being overwhelmed. So typically, by having the virtual prototype running within an environment, we get this visibility of seeing the software alongside the hardware. We get to see the events as they happen in both of those regions. So we can see interrupts happening in the hardware, how it impacts the software, what software functions running when, what software function may be using the most power. So we can really get a good insight into both of the different domains that are involved within this system by having this single viewpoint of both the software and the hardware. Typically these days things are multi-core, so it's important that the virtual prototype copes with multiple cores and maybe even different types of CPUs itself on the same platform. So it's important that tools can recognize the cores and help present where the loads are, what cores doing what, whether things are waiting, and helps you debug on multiple cores. Again, all of this is hugely beneficial using a virtual prototype as compared to real hardware, which becomes very complex when you're dealing with multi-core platforms. So hopefully I've kind of walked through quickly some of the values that we can gain by using virtual prototyping technologies. So obviously it should help shorten the overall combined product lifecycle by enabling the software teams to start integration and development of software very early in a transparent way, so without changing the existing software flows. Providing a fast and deterministic execution of real software. The non-intrusive capabilities are very powerful to collect and analyze performance data without actually impacting and instrumenting any software image. And because it's virtual, it can be changed very quickly. The hardware teams can turn around new virtual platforms very quickly, changing perhaps parameters, timing power policies. It's only ends up as an executable file, so you can share it very quickly and deliver a virtual prototype across the network, and it makes life easier. So if you'd like any more information on some of the topics, then please get in touch, and I'll be glad to talk more or demonstrate some of the tools and things that I've talked about. And if anyone has any questions now, I'll be glad to try to answer.
Yeah, thank you very much, Mark. I think we're going to start in Bristol with the questions. So any questions in Bristol? I have one from Jeff Barrett, so I'll just hand you the mic.
So is there anything special about the FPGA platform you're using? Is that you know, custom for this sort of application?
Talking with my mentor hat on, we do have a partnership with a company called SoC, where we have some technology in place to kind of bridge the TLM transaction to the FPGA board using an AXI kind of transactor. So we do have a partnership with a particular type of FPGA board, but you know, we can, hopefully the process should be fairly generic, and the same types of process should be able to be applied to other types of FPGA board.
So how does that system compare to Veloci in terms of its performance across Scheme, for instance, and its price point?
Yeah, obviously FPGA board's much cheaper, more affordable. The performance is I believe actually can be increased to what you would see on an emulation. It just depends on what you've got on the FPGA board. If you're interested, I can set up some additional talk or demonstration about that. To be honest, I'm not a true expert in that area, but I can get you some more information on that.
Okay, thank you.
Thanks.
Jeff hinted at something there as well, Mark, about Scheme. I'm not sure whether it's explicitly mentioned, but the TLM across into the onto the emulator, is that all done via Scheme?
This is done using some kind of transactor that's kind of comes with the Veloci in this case. So we can talk to an emulation guy to get the specifics on that.
Sorry, I didn't realise. I think from what you're saying, the answer is yes. Anyway, sounds like a transactor going across to a synthesizable driver.
Yes. Yeah.
Any more questions from? I was a bit scared about your printf, by the way. I'm going to have to do my debug in a different way, by the looks of things. I think we're going to see if there's any more online. Okay. All done? Okay, thank you very much, Mark. Thank you.
Thanks for your time, everyone. Thank you.